All right, last day of the conference, last discussion session before lunch, and we're going to be talking about our codes.
And your codes.
So at first I was a little worried about this because, you know, it's a lot of you may not care about our codes. You just care about our results. But I was talking with Mark about this, and I realized one of the advantages we have is that this discussion can, you know, be primarily led by a lot of the junior people in the room, because you're the ones that are actually running these calculations. You know, it's not Dong Lai or Steve Lubo that are actually up at 1 a.m. trying to figure out why their code is crashing. It's these junior people. And so we really want to make sure that the discussion is really, this I think session more than any of them you can be led by you guys. Anyway, this is our code comparison project that we're doing. How do I go to the next slide? All right, that's fine. So the idea is we have all these different codes. They're all running this ostensibly the same or similar problem. Just the question Magda asked right at the end of the last session, how can we be sure that we're converged? How do we know we're getting the right answer? Ultimately, that's a very subtle question. But one thing we can do to work towards that answer is to ask, can we get the same answer to the same problem? So I want to also say this is not what we're doing is not a code. We call it a code comparison, but we're really not trying to find out whose code is best, right? There's not going to be a thing about, well, you have to use this type of code. You need a moving mesh in order to do this. No, it's really just about, if we do exactly the same problem, can we agree on the solution? And that will at least give us some confidence that what we're doing has meaning. And then the other part of the question is, what do we need in order to achieve that solution, that agreement, and if it is the correct solution, to get that correct solution. And so what we're going for then is actually, in order to get that agreement, we're actually going to the minimal binary problem we can. So as simple initial conditions, as simple a setup as we can possibly write down. So all the things that everyone in this room hates: 2D, circular, equal mass, binary isothermal equation of state, Navier-Stokes viscosity. And part of it is just uniformity across all codes, but also I would argue there's still disagreement in the room about this problem and about what those solutions look like for this most basic version of the problem. So then the question is, if we're doing exactly the same problem, you expect we should all converge to the same answer, but we haven't explicitly really tried this yet, like using a bunch of different codes and do identical initial conditions. So that's what we're doing. And even this problem, even this most minimal basic binary disk problem by itself is numerically challenging. And I'll show you an example of that. Thanks, Mark. Well, don't worry, you'll get to talk in a second. We're only going to do this for like 5 minutes, and the rest will just be you guys talking. But I wanted to illustrate why this is such a hard problem. So this is actually something I did just last week, because we're starting to set up our initial conditions. And so I wanted to I wanted to just do a little quick demonstration of why this problem is so hard. So all I'm plotting is we haven't completely converged on what our initial conditions are going to be, but I've set up what we've decided on so far, and I ran it. I ran this code. Used my code to run it and plot the torque as a function of time. And so the top panel there is at 1 orbit, and you can see these different colors are different resolutions. And never mind what 64, 128, etc. mean exactly, but they mean basically I'm just doubling the resolution. And so the top panel looks like what you'd see in a code paper, like really nice, obvious convergence towards a solution. And that's not too hard to imagine why you could do that for 1 orbit. And I'm hoping that, you know, a few of us, Matthew and some others, have actually already done the 1 orbit test to just check that we get the same answer. But then once you go beyond an orbit, things start to get a little bit messier. So you can see that the 64 and 128 runs are a little bit of a mess. The other three, the higher resolution runs, all seem to look like they're doing about the same thing. So you'll notice the torque is negative. We're only doing 10 orbits here. It looks like the torque is negative. That's kind of interesting. Well, it's 10 orbits, so who knows? Then once you go on to 100 orbit time scale, you can start to see this instability in the disk that have been talked about a lot in different contexts. Some people refer to the lump or the asymmetric cavity. They're all sort of caused by the same underlying instability we don't have a name for. Maybe we should call it the McFadden instability, because that's my advisor who came up with this. I'm a little biased, but I think that would be nice. But anyway, it starts to get, the variability in the torque gets very large, and so you have to time average. And you can ask, oh, this looks kind of like it's in a steady state, and it's getting a negative torque. That's interesting. This red is the time average, sorry. And then you can say, is it in a steady state? Okay, I'll run it for 1,000 orbits. Let's see. Looks like I've got a nice negative torque in a steady state disk. That's interesting. But then, if I instead just all I do is double the resolution. Yeah, sorry. This was my 256 run. This is my 512 run. Looks good. I'm getting a negative torque, time averaged. Everything looks fine, right? Let's see if I run it on 1,000 orbit time scale. Oh, now the torque is positive. Oh no. So this is really tricky. It's basically saying, this is not like a lot of things. Normally when you think, okay, I'm not quite converged, maybe I'll be 20% off, right? But if you don't do this carefully, your sign can be wrong. And this is a recipe for confirmation bias, right? If you're looking for a result and if you're not careful, you can find it. So you have to be very careful, and we don't really yet have a standard for exactly what resolution and time scales you need. We say roughly a viscous time or something, but we don't yet have a very good clear standard for that, and how it depends, for example, on the Mach number. But it's an invitation for confirmation bias, and so you can add all of the missing physics you want into your code. If it's not converged, you might as well be mining Bitcoin. So, yeah, go ahead, Marky.
Sure. So most of the codes, as you may have gathered, for the so yeah, they're well. Maybe you want to take this slide.
Oh, sorry, we don't have your. Why don't you just?
I'll switch over to mine.
Okay.
Do you want me to switch?
Yeah, sure. Sorry.
I think I can basically say in words what's on my slide, so I don't have to waste time finding it. So I spend most of my time doing these 3D GRMHD simulations, and we're never going to get to tens of thousands or even thousands of orbits in the next couple of years, maybe thousands of orbits. I mean, Scott's really pushing in that direction. So why be involved in this code comparison project? I think there's a lot. There's a lot of opportunity for comparison, even in just thinking about the details of what's going into the 2D problem, and then we can start to try and take the next steps into 3D. So also, I wanted to say that there are big code comparison projects that have been done that I think we can take a few lessons away from. So one of these that I'll just focus on is the Event Horizon Telescope Code Comparison Project, which many of you I'm sure are aware of. And there they took a initial hydroequilibrium torus in 3D, started a field loop and 9 different groups with 9 different codes, tried to run the same physical problem with as much of the boundary conditions the same as possible. And this was really motivated by the simulations from different groups that would be in comparison to the data from the Event Horizon Telescope. And so seeing if there was a converged result on what ultimately the radiative output predicted from the simulation should be was an important step there. How long do you need to run? What types of resolutions are required for the different codes, etc. So that code comparison project took about 2 years, but I think we're hoping that because of the the maybe simpler nature of the problem in some aspects, 2D, much faster to run, cheaper to run as far as computing time, and the advent of this workshop, we can cut that time down, at least to decide on the initial parameters of what the problem will be, which I think is the big crux. And then groups can go out and work on these in different ways. So I wasn't involved in the Event Horizon Telescope Code collaboration, but I worked with people who were, and I sat down and chatted with Scott and reread the paper. And I think a few of the key takeaways are, one, finding a key motivation to make people want to spend their time, or as students want to, get involved in maybe picking up a new code and being involved in this project. But then as organizers of the code comparison, being forgiving to some degree with schedules and those types of things, but trying to frequently iterate, and that kind of thing. So tolerant of people's schedules, but also trying to keep a cohesive momentum moving forward with meetings and that kind of thing. And so KITP is a good place to start this at the workshop. Another key lesson, I think, to be taken from the Event Horizon Telescope Code Comparison was that it's really important to have at least some key differences in the way the codes run the problem, even if the physical setup is the same. So specifically, for instance, having a Cartesian code involved to be compared with cylindrical coordinates, or a code that generally runs in spherical polar coordinates or something. And I think we have that already here with Mara, so that's good. And please, if you have other thoughts on lessons that can be taken from the Event Horizon Telescope collaboration or others, speak up. Yeah.
All right. So, good. We already have a question. We'll go straight to you. But we could just put this slide up with questions and then just get to questions rather than hear me talk anymore. I think that everyone would prefer that. So maybe we could go straight to Judith.
I would like to come back. I'm Judith Suladi, by the way, from Switzerland. I would like to come back to this resolution problem. So I have static mesh refinement, therefore I have for free resolution comparison on the different levels. And I did find that you get more and more correct solution the higher resolution you go. And you can even understand this why. First of all, your numerical viscosity going to be smaller if you have higher resolution. And this is also goes back to whether Cartesian or spherical or polar or whatever grid we have, and what are the shapes of the cells or wherever. It comes back to the numerical viscosity, and that's going to change your accretion rate, your torque. So I think the number one question would be measuring the numerical viscosity in our codes. That's going to give us a little bit of a handle of how much the results are influenced. Now, the second thing is that what is the correct solution? So when we have radiative simulations, we find that if you have higher resolution, the temperatures goes higher since you go deeper than in the potential well. So what is then the final temperature that you need to achieve? In my opinion, the radius of the object, it should be resolved on the finer level. So I'm doing, planets, so that would be the surface of the planet. And then we get the correct temperatures, the correct rotation around the object, and then we get a more correct solution. So I believe that that's the resolution we need to achieve somehow, either nested meshing or whatever you use in order to get correct results, because otherwise, what do you measure, really?
That's great.
Yeah.
There's a question online.
Yes, sorry, there's a question online from Jinlu.
Yeah, so I just wanted to say, as an observer, I would like to ask 2 items on my wish list. Well, I have more, but I'll just ask 2. So the first one is, I think related to the code comparison issue, is that I think, as Tamara pointed out, an excellent point the other day, as we have these interesting candidates, so for example, from periodicity, we would like to have complementary tests in terms of the observables. And one thing I find it to be challenging is to be able to find a self-consistent model that gives you the prediction on different fronts. So for example, when we try to use the periodicity model, like to infer the binary parameters, then we also would like to understand the SED features, such as hard X-ray access or the thermal dip in the circumbinary gap opening. But it seems to me that I understand that different studies tend to focus on different predictions. So either on the periodicity or on SED features. But I would like to have perhaps ideally a one-stop shop for everything, so that you can have the self-consistent model. Because like at least for one particular target, like we weren't able to find a self-consistent model that can explain both the periodicity and the SED feature that we saw. And we weren't sure if it's evidence that is just not a binary, or it's due to the fact that different models are not really self-consistent. So that's one question. And the other thing I would like is, like similar to the EHT, right? So, or actually also to LIGO, they have these templates, right? So they, for, perhaps waveforms for EHT, they have templates of the images, right? From GRMHD simulations. As an EM observer, I would like to have also a template or a library of, for example, the predicted light curves, so that I can do a full, proper parameter space search whenever I want to compare observations with models. Because right now I cannot do that. Like I only have very limited predictions to work with.
Thank you very much. That's very good. In fact, Zoltan mentioned something similar to us in the about this. I don't know if you wanted to comment or.
Yeah, just two quick comments. I think it would be great to add some diagnostics to this code comparison, which relates to the observations, like the m-dot periodogram. The other quick response, Chin, very good point. Maybe just for everybody's aware, we have this so-called multi-messenger work package group in LISA, in the LISA consortium. And this is exactly one of our tasks, to assemble electromagnetically relevant predictions from binaries. And anybody who's interested in contributing to this should definitely talk to me, because it's going slow. I mean, it's obviously a big project. But what you outlined, Chin, is a very big project, basically, to assemble such a library of predictions.
Yeah, thank you for leading that effort, Sultan. Yeah.
But it's starting to maybe happen in this work package, and we can use more help.
Caitlin, did you have something?
I'll let Xiaohan go first.
Okay.
Yeah, so I'm from the planning interaction community, and there were 2 code comparison projects have been done over the past decade. The first one was very similar to your setup here. It's a 2D planning in disks. And that time, there actually is very beneficial to do that, because there was the discovery of the vortex at gap edge. It was confirmed by that project. At that time, people do not know whether those vortex were real, or it's by instability, or it's numerical. So all the code did the same setup, and they all see the same thing. So it was very beneficial back then. The second project was started 4 years ago, but we haven't finished it yet. So that's kind of a little pessimistic on the time scale. And that was doing a 3D simulation with planning in the disk. So that takes much longer to do. And also nowadays, since half the code got one solution, half the code got another. So that's why it takes time. Regarding the setup, in both projects, really need to define a very well-defined problem. Like not only initial condition, but the boundary condition needs to be well defined. And also in our problem, how the planet mass is introduced, we need to give the exact same sign function for every code. And when you calculate the torque, we need to say what kind of a region needs to be excluded, what kind of a region needs to be included to get this torque. So not only on the simulation itself, but also on the diagnostic needs to be all the same. And the resolution needs to be specified. The different codes needs to have the exact same solution. If it's using a different grid, the different grid needs to have the same resolution, equivalent resolution at some radius. Yeah, so that was for the planet disk in action.
I totally agree.
So can I, yeah, and to, so this is related to this. So yeah, I agree with everything that Xiaohan just said. And you know, I think we've talked about some of these things and tried to write them down. The other sort of semi-philosophical question I want to ask is related to, you know, this issue of how long you need to run for to be in steady state, and how do we connect that up with what the actual problem is at hand? So for example, if you run for 1,000 orbits and get one answer without moving the binary, and after 1,000 orbits, the answer changes, like, are you no longer solving the right problem because it was inconsistent to hold the binary in that location for 1,000 orbits, and now the answer has changed, but maybe you're getting an answer to a different problem now because of the way that the initial setup is involved. So this gets back to this issue of a live binary or a moving binary, but I really think we need to think about, you know, should we expect a steady state for that many orbits in the real system?
Yeah, I totally agree that even though we're just looking at code comparisons, we can still learn something about the system based on what we need to achieve, you know, the steady state. That also tells you something about the system. Yeah, I totally agree. Prioritize Magda here.
Yeah.
She's.
I wanted to ask about comparing different codes. So have you thought about, or have you found a solution to comparing mass-based refinement versus volume-based refinement? So I work with mass-based refinement in the circumstantial disks, which I think is now kind of clear as a region that significantly impacts the torque. So how do we actually make sure that our resolutions match up if you use volume-based refinement grids?
Yeah, so we have another question, but maybe Scott, can you comment on the resolution choices made in the EHT code comparison, or someone in a different project?
EHT was pretty, it's relatively homogeneous in their gridding. There were, I mean, the two differences was a Cartesian grid versus a spherical grid, and it was all, some had fixed mesh refinement, and in that they had more refinement near the equator. I don't know if Sasha wants to comment about. I know there were some hammer results, but I think there was some mesh refinement used. I don't know what it was like specifically, but nothing like mass. Mesh refinement based on the mass is mostly by the volume. But I don't know.
No, I think. Oh, yeah, 2 words and then Bhupendra.
Use refinement, yes. Yeah, that was 3. So we do use mesh refinement, but what's most important, at least the philosophy that we adopted, is we try to refine most of the volume where the disk is concentrated. With a single level of refinement. So you can, I guess, basically we have a density floor. I mean, not density floor, but density-based criterion. If density is above a certain threshold, which we choose for a particular problem to basically select for the disk body, then we refine all the way to the maximum refinement level, so that the turbulence is refined uniformly everywhere. And we also make sure that the cells are cubical. Sorry, that was more than 2 words.
That's fine.
This is Bhupendra again. If I remember correctly, the HT code comparison, despite having the similar initial setup, the final steady state m dot was very different for different codes. that goes back to very first question that probably we should first worry about achieving a steady state m dot and making sure that different codes do not differ by factor of 5 or 10.
We have a bunch of people online.
I'd like to return the conversation to the question that Caitlin asked a few minutes ago. And that is the issue of the long-term qualitative change that you saw. In all of these simulations, there's a finite amount of mass on the grid. And so after a while, you could have a global change as if you're consuming some significant part of that mass. So when you looked at this change on the longest of timescales, did you see anything happening in terms of both the quality of inflow equilibrium in the inner disk, where the most important things are happening, or the total mass of the material on the grid?
I'm going to give a quick answer to that question, then we'll go to the people online. The quick answer is no. The disk is being fed from an outer boundary and you achieve a steady solution. Is this just the order that they go in, or? Okay, so I guess it's Roman then.
Hi, I have some comments about the diagnostics. I mean, since people were asking about which diagnostics to use. In my own experience, working with different people, I found that sort of highly processed fluid variables are very good as diagnostics of what's going on in a system, especially in a system like circumbinary disks, where you have this giant exhibitor in the center launching waves. So in particular, angular momentum flux of these waves is a very good diagnostics of let's say resolution of various conservation laws and so on and so forth. And I really advise different codes to look at things like that, like angular momentum fluxes of the waves, which are propagating out, let's say, in a disk. Another thing, another sort of good basis for comparison are quantities which should normally be conserved, under some idealized conditions. For example, vorticity or potential vorticity. We know that in the absence of the shocks, vorticity should be conserved, and it would be non-conserved if you have shocks. So essentially, comparing structures in potential vorticity that your code produces would tell you about, for example, how different codes are capturing shocks and so on and so forth. And finally, I would also mention that it's good to sometimes set up at least some problems which can be tested using linear theory. So for example, you could create a disk with a big cavity and put in, let's say, some small mass perturbers. So there is a small mass ratio, in which case the waves would be linear, and you can just use WKB theory or linear calculation of the wave properties in this system to compare with, how the codes are comparing. I mean, that in this case would be the correct sort of semi-analytical solution to which the code should be tending. And that also tends to be quite useful when you are doing this, trying to see the performance of your code.
Thank you, Roman. I knew you were going to say angular momentum flux, but that doesn't make it any less important. Jeff.
Hello. So I had a couple of things. One, I think I'm contractually obligated to say that one of the things we should consider sort of varying or specifying is the sync prescription and how it treats angular momentum, especially with what Matthew Bates has been talking about and experiences in earlier protoplanetary results. This also seems like it would be a great opportunity to invest in running one of these things with our code for a super long time, like well over 10,000 orbits, to sort of get some very long time scale. Clearly not everyone will be able to do this, but it'd be good to have, I know in the EHT there was some reference simulations done with Hammer. And I think if we could do something similar here, that could be cool. And if you're running for a longer time, it might be worthwhile thinking about whether or not an initial J dot should angular momentum flux should be imposed throughout the disk from the initial condition. Normally we initialize with zero initial angular momentum flux, and sort of we let the binary tell us what it should be. But you know, the binary imposes an inner boundary condition, and then we have our outer boundary condition, which is feeding in. At some point, these things are going to mismatch, and if we're trying to get something reliable in the end, then we might want to impose a J dot from the beginning.
Yeah, if I can make just a very short follow-up comment, I was going to say that one of the things we had discussed is trying to focus in this project in converging on the physical system, and then to some degree letting people set it up the way they've been running problems as a first step. And then if we see some differences, then we can really pay attention to angular momentum transport at the outer boundary, where the outer boundary is set, and the sink and those types of things that you were talking about being very important. I love the idea of having the benchmark be very long as opposed to like very high resolution or something, but great. Thank you.
All right, Manuel is next.
Okay, so I want to mention maybe a couple of comments here. So I come from in a community, the numerical activity community, that traditionally has been doing this code comparison since now more than a decade. And we have learned to work well together, but I want to remind this community that in vacuum, even if GR is complex, I mean, our set of diagnostic are much simpler, and the codes are much more uniform than what we have here. So the codes that we're talking here are far more disparate, have many more differences. It might be more useful if we focus on these diagnostics that Roman mentioned, and we can come up with a set of diagnostic that we all agree that an MHD code, a GRMHD code, has to pass, whether it's Cartesian, whether it's spherical, and so on. I think if we can all agree, and this meeting, this workshop would come up with such a list, it would be really useful, more so than actually the code comparisons, because of the details that, there's too many details that are different in these codes.
Paul, do you want to comment on the spreadsheet where different capabilities and setups are being listed?
I don't know what I'd say other than, yeah, there's a huge variety of the types of codes that we use to solve these problems. There's a lot of work in establishing some kind of uniformity in the problem that we're doing. But yeah, thank you for that comment. Sorry, if you want.
Yeah, I guess we have talked a bit about diagnostics, but I think you were saying specifically that we do this code comparison and we choose some diagnostics, and we should also think about those diagnostics being handed to adding more physics like MHD, and MHD then having to pass those same diagnostics. Was that what you were saying?
Yes, I'm emphasizing the fact that if we decide on a set of diagnostics that codes need to pass, okay, and there might be difference whether you are in a 2D or 3D, and some might overlap, but then we decide which are the ones that we think are important to resolve the MRI, to get M dot right. I think it would be much more valuable, because then people, and then you can post your diagnostic somewhere, but then people will know exactly what to do instead of going, and comparing codes. Because in the comparison paper you mentioned, Mark, I mean, yes, it was useful, but I'm not sure we did learn a lot about, which code is really performing better than others. So I don't know if we learned to the details that we need to learn here.
So, okay,
it should be a good stepping off point. Not only should we make 2D agree, but it should be a stepping off point to.
Yes.
Yeah.
So yeah, I think that's right. I think one of the advantages of having all these diagnostics is that someone who has never run a binary calculation before has something to shoot for with a given initial condition, and knows what other people in the field already agree is a converged solution. So yeah, thank you for that comment.
Yeah.
Oh, sorry. Yes, Nicholas.
Yeah, hi. So this is a good segue as someone who has almost never run a binary simulation. So I come from planets, and I was just maybe wondering if in your comparison, are you planning to, in the simplest case, include these mini disks around the binaries? Because I think from reading some of the literature, different types of codes might have difficulties, well, more or less difficulties resolving these regions. So would it be worthwhile maybe starting with the simplest case where you exclude this central orbital area region of the binary and just see if what's going on with the cavity, you know, this eccentric instability and all these things, if you even get agreement on that problem with different codes and different resolution?
Thanks. That's a great point. I would say it's debatable which one is simpler, whether you excise the binary or not. But I think it's a good idea to try to include both perspectives and see if you can get the two to agree.
Yeah, the importance of including the central cavity region for angular momentum transport is maybe a science problem that we can stumble upon without even really trying if we do the comparison of both cases.
Mm-hmm.
Any other comments on how we might make comparisons between 3D, say, SPH simulations, or set up something that is very close to equivalent, or is close to equivalent to the case that the 2D problem can solve?
Well, we're running to lunchtime anyway, so we'll probably lose the room if we keep going, unless we have other comments. Oh, yes. Oh, yeah, I'm sorry. We do have a Slack channel for this, for the code comparison. It's an ongoing project over the course of the whole program. It's just code comparison, _comparison, right? We can post it somewhere.
And there's an overleaf link in there.
And there's an overleaf link that lists so far what we've written down as our initial conditions in as specific form as possible, and we're still working on that.
And there's also a spreadsheet where if you don't want to run a new simulation, you can give us information about simulations that you've already run that we can then include in our general comparison.
All right, thank you all.
Yeah, thank you. I think time for us.